All right, here we go. What's up, team? Rich with Kestava Engineering, bringing you another midweek mini. This one is from a request of someone who is currently doing a semester project, and they are designing a building, which I think is pretty fantastic. And they right now are trying to figure out how to design for seismic demand. So I'm going to give them this little practice problem today for a multi-story structure and how to distribute their lateral forces under seismic conditions. Let's jump in. So we have here around the square perimeter of a 12-story building is a series of special street moment frames. The floor loads and the frame dimensions are shown. So we have all of our stories here. Each story is 13 feet typical, and there's 3 bays that are 30 feet wide each bay. And again, they said it's a square, so that's 90. If you look in plan, that's 90 by 90. You have your height above the first floor in feet, and then you have your total story dead load in kips. So at each floor, that's the summation of dead load for that floor. They did also ask me how do I calculate dead load and get my seismic mass. That's going to be another video coming up. I wanted to make that completely separate. So let's just start with this today. We're given those that seismic mass at each floor, so we're going to roll with that as is. Plenty to do in this anyway. We're given a couple things here. An occupancy category of 2, site class of D, importance factor of 1.0, an SS of 1.0, and an S1 of 0.4. And we have 3 questions today. Number 1 is calculate the story shear at each floor. All right. Number 2 is calculate the overturning moment at the first floor due to seismic loads only. And then number 3 is calculate the overturning moment at the 4th floor due to seismic loads only. So let's get going with question number 1. So we need that. How do we find story shear at each floor? So in my previous seismic videos, little thumbnail right above there, if you want to check those out, we went over a single story structure and we found our base shear. And technically, we did distribute it to story shear, but since it was just one structure, it seemed pretty straightforward. This time, we have multiple stories, so let's see how that gets broken up. So first, we need to find our base shear before we can find our story shear. So let's get going. Today, we're going to be jumping into the ASCE 716, and we're going to be using chapters 11 and 12, because, we're in seismic design right now, so that's what we got to do. So first, we're going to jump over to Chapter 11 of the ASCE, and we're going to head to Table 11.4-1 and 11.4-2, because we need our FA value and our FV value. So let's go get those. So here we are, Section 11.4, Seismic Ground Motion Values. So we need to go through Chapter 11 before we can jump into Chapter 12. So let's jump down through here and see what we need to get. I know this looks super familiar to you guys. We just did a 3-parter last time, so you guys are pros already. Already know this. So let's get going. So here we are. We just start at the very beginning here. So we need SMS and SM1. And like I said, that in order to get those values, we need FA and FV. So here we are, table 11.4-2. Let's find FV first. And we have our site class of D. That's already given. And we have an S1 of 0.4. We're just going to scooch down, 1.9. All right, so FV, 1.9. Scroll down, let's find FA. FA, same thing. Table 11.4-1, site class D, SS of 1.0. We're going to scooch down, scooch across of 1.1. Whoa! But hold on a second. Remember, check up here in our notes where we have site class D, as default site class per section 11.4.3, the value of FA shall not be less than 1.2. You'd think you needed to use 1.2 instead of 1.1, but here's an even more of a screwball for you. It says if it was selected as the default site class. So in this instance, we're going to say in this problem that it's known through geotechnical analysis. It wasn't just the default because of unknown information. So we're going to get to continue to use 1.1 for FA. So equals 1.1. Now, above, we can find SMS and SM1. So let's head back. SMS is going to equal FA times SS That breaks down to 1.1 times 1.0, which equals bada boom, bada bing, 1.1. Next, we can find SDS, which is 2/3 of SMS. That is 0.73. SM1 is going to equal FV times S1, which is going to equal 1.9 times 0.4, which gets us 0.67 or 0.76. Now we can get SD1, which equals 2/3 of SM1. We all know this. We fly through this. That is just 2/3 times 0.76. That comes out to 0.506, so we'll just round up to 0.51. All right, now that we got all these suckers, now we're going to head over to table 11.6 -1 and 11.6-2. So I will see you over there. Here we are, 11.6-1 and 0.2. All right, so seismic design category based on short period response acceleration parameter, or SDS. So our SDS, I already can't friggin' remember, so let's go back. Wow, there it is, 0.73. Okay, let's go back. 0.73, obviously knew that, so we fall into this category, greater than 0.5. We're risk category 2 from our problem, so we're D. And we can check the bottom table as well. So this is our based on 1 second period response acceleration parameter, SD1, and SD1 is greater than 0.2. I think it was 0.51, so risk category 2 again. Wow, D, we're good. So we are seismic design category D. Next, since we have that, now we're able to move on to chapter 12. And in chapter 12, we're going to go to table 12.8-2 and use equation 12.8-7 to get the approximate fundamental period of our moment frame structure. See you over there. Here we are, section 12.82, and in order to determine our period, we can go below here, and we're using equivalent lateral force procedure, ELF. So we're going to be finding the approximate fundamental period, denoted as TA, using this equation. So we need a couple of variables here. Those variables we can find, boom, right here in this table. So CU, first we're going to find CU, and that's based on SD1, or SD1, I can't freaking remember again. SD1 is 0.51, duh. So we're that category as well again, so CU is 1.4. We move down a little bit further to the next table, 12.8-2. Now this is based on our structure type, so we're finding C sub T and X, and our structure type is a moment resisting frame system. Wow, word for word, how did we do it? Moment resisting frame system in which the frame resists 100% of the required seismic force and are not enclosed or joined by components that are more rigid and will prevent the frames from deflecting where subjected to seismic forces. That's our guy. And we're steel moment frame, none of this concrete. Get that out of here. So we're doing steel. We have a CT of 0.028 and we have an X of 0.8. All right, lovely. Let's go bring all this back. I feel we're getting ahead of ourselves here. So TA, approximate fundamental period, is C sub T times HN raised to the X. That's going to be 0.028. The height of our structure, well, the total height is 156 feet. That's up to the roof line, so 156 feet, H sub N, and then X is 0.8. That's going to get us 1.6 seconds as our approximate fundamental period. Now, I said before that we're using the equivalent lateral force procedure, but we need to make sure that that's applicable for us in this scenario. So we need to go back into our code, and actually we're going to flip over to table 12.6-1, which is on page 100. See you there. Here we are, page 100, table 12.6-1. So this is where you make sure that your procedure is permitted based on the type of structure that you have and this type of design category you're in, your seismic category, your risk category, all that kind of stuff. So let's take a look. So seismic design category, well, we're D, and it's friggin' all of them besides A. So we're D. And then if we look down here, we are all structures. Oh my gosh. Well, we're risk category 1 or 2 building, not exceeding 2 stories. That's not us, unfortunately. Structures of light flame construction, that's not us. Structures with no structural irregularities and not exceeding 160 feet in structural height. Well, we don't exceed 160 feet in structural height, but we're not sure if we have any irregularities. So, sorta, that's a question mark. Structures exceeding 160 feet in structural height with no structural irregularities and with T less than or equal to or less than 3.5 T sub S. Well, let's go to the next one because we're still not sure. We don't exceed 160 feet. So we'll go to the next one. Structures not exceeding 160 feet. Okay, that's us. In structural height and having only horizontal irregularities type 2, 3, 4, or 5 in table 12.3-1, or vertical irregularities type 4, 5A, or 5B in table 12.3-2. So there's a lot going on there. So a little trick we can do here for this problem is if we choose this one, even though we don't exceed 160 feet, it means that we still pass that parameter because we're less than that height, so we're okay. And all we have to do is make sure that T is less than 3.5 T sub S. And if you look up T sub S on page 82 under your symbols, let's head there. Here we are on page 82. You see here, T sub S just equals SD1 over SDS. That's easy. So let's plug in for that. SD1 over SDS is going to equal 0.51 over 0.73. That is going to equal 0.698. And we were told to make sure that T needed to be less than 3.5 T sub S. T sub S equals the following: 2.44 seconds. And we know that T is our T approximate, and that is 1.6 seconds, which is less than 2.44 seconds. So that's us, and we pass. So if we head back to our table to show permittance of what procedure we use, let's see if we're okay. Here we are back here, page 100. So we know that this criteria works. And if we look up equivalent lateral force, ELF, we see we get a P, which means permitted. So we are good to go. And even though I had to jump all the way back to page 89, I'm seeing this right now because I'm a friggin' idiot. But you know what? I'm learning just as much as you guys. Look at the footnote here. It's like they knew. P is permitted, NP is not permitted. Oh, T sub S. There's our beauty. Now, let's find C sub S. Let's get to the meat of this problem. So if we jump down, so here we are on 12.8, equivalent lateral force procedure, because that's where we're deemed we are permitted to use it. We know that base shear, seismic base shear, denoted as V, is equal to C sub S W. Well, we need that C sub S, and we need W, which is our seismic mass. Let's find C sub S first. So C sub S, we scroll up here, equation 12.8-2, and we see it's under this following equation. Well, we need R, and we need I. R is the response modification factor, and I is the importance factor. I, we know, is 1.0. That was given to us. R, we need to head to our table 12.2-1, which specifies the response modification factor, R, based on our structure type. So let's head over there right now. Here we are, table 12.2-1. Let's scroll down here. We've been here before. We know what we're doing. Well, let's see what we have. Building frame systems, steel eccentrically braced frames. No, we're looking for moment frames. Okay, so here we go. Moment frames section. And right at the top there, steel special moment frames. We're going to assume in this problem that we're using special moment frames. There's almost absolutely no way that you're not permitted to use ordinary moment frames for the height of the structure that we have. That's in the code, but I'm not going to get into that right now. And then you might say, well, you got intermediate moment frames. Well, intermediate moment frames are basically almost special moment frames, except you don't get nearly as much of the benefits. So your detailing and your cost to construct them and the cost to design something for intermediate moment frames takes almost as much time as special moment frames, but special moment frames, you get so much more resilience out of the system. It's very rare that you see intermediate, but leave a comment in below and let me know if you think otherwise. I'd be curious to hear what you have to say. So we're going to be doing number 1, steel special moment frames, and that's an R of 8. And we could If we were going further in this problem, we could take our omega and our c sub d, but we're not going to do that. Instead, we are just going to take that response modification factor of 8. Okay, tabulate all this, and let's get back. So c sub s going to equal SDS over R over IE. Plug all that in, gets you that, which equals 0.09125. Well, now we also have our maximum c sub s. So for conditions where t is less than t long, so long period, the long period, let's just assume we're rocking and rolling the Pacific Northwest again, because I forgot to mention this. That's totally on me. But the long period I know is 16.0 seconds where I'm from. And our t approximate is, what is it? 1.6 seconds. Oh my gosh, we fit into that category, like always, but, I didn't say that. All right, so that means that C sub S max, based on the equation SD1 over T times R over R, IE. T being approximate, so TA. Plug all that in. SD1 is 0.51. TA is 1.6 seconds. R is 8 over 1.0. That gets us 0.0398. All right, so 0.0398 is the max that we have to consider C sub S. Well, above right here, we have a larger number than that, so we can ignore that, which is really nice. So our C sub S is going to equal that value right there. And let me just jump back to the code to show you where that C sub S max equation came from. All right, here we are on page 101. So we had our C sub S equation beforehand. We knew that R equaled 8. But then right down here, that's where we knew that T was less than T long. So we got to use this equation. And if we see in this note right here, the value of CS computed in accordance with equation 12.8-2 need not exceed the following based on this equation. So that's where it came from. And they also have C sub S shall not be less than. So you know what? Let's be good Samaritans and let's do that one as well. So let me flip over. I'm just going to do it over here. CS min going to equal 0.044. SDS is 0.73 and I is just 1.0. That's going to equal 0.032. All right. So we're fine. We're nowhere near less than that. If you're going through this and you might be a first timer or whatever, and your professor gives you a problem with just totally random made up numbers, like mine are all made up. If they're made up numbers and it gets you and you get a CS min where that controls, you might want to do some mental math, go back, check a couple things, make sure you're square, because that almost never, ever happens. I mean, you can see how low this number is. Just watch that. I mean, they provide it in the code, obviously, but this shouldn't happen, really. I mean, I guess you could say in seismic regions that aren't controlling really that much, but you still have to check for it based on maybe a special type of building. Maybe that's where it comes in handy, but this almost never controls, ever. So just my word of wise there. All right, let's keep going. Now let's find our seismic mass. Well, big W for Wumbo is just going to be the summation of all of our story masses. So if we scroll up, all of these bad boys. So all of those summed together will be 18,500 kips. So big W, 18,500 kips. Now we know that the base shear from equation 12.8-1, I already showed it to you, so I'm not going to go back to the code. This one's a easy peasy. We got W, we got C sub S. That's just going to be 0.0398 times 18,500. That is going to equal 736.3 kips of base shear. And there we go. Now we have to distribute that to each story. And to do that, we're going to jump over to equation 12.8-11 and 12.8-12, where you have the following. F sub x equals CVX times V, which is our base shear, and CVX is going to equal w sub x, so little w sub x, times h sub x raised to the k, all over n for your number of stories. I to the 1, this is just some nomenclature, mathy, woohoo stuff here. Don't really worry about it too much. I'll explain. H to the I raised to the k. All right. Well, first, the only thing we don't have is k and k. So for k, let's go jump over to the code. And we're going to head over to 12.8.3. So we took down that first equation, took down the second equation, and now we're looking for k, which is down here, based on this criteria. So like I said, 0.1 s or less, k equals 1. For periods of 2.5 s or more, k equals 2. And anything in between, you interpolate. T sub a, our period, is 1.6 seconds. K equals 1.0 at TA equals 0.5. And k equals 2.5 for frick! K equals 2.0 for a period of 2.5. Well, 1.6 is what we got. So if we plus 1 to that side and we minus 1 from that side, that gets us 1.5s. That's close enough for me, so k is going to equal 1.5. All right, so now we have everything. So now we need to go ahead and determine our values of the equivalent lateral force, F sub x, computed by the above provisions that we have. And we're going to tabulate it as follows. So buckle up. We have level. We have W sub x. Let's fit it in better. We have W sub x. That's in kips. We have H sub x. That's in feet. We have W sub x, H sub x, raised to the k, which is just 1.5. And then we have F sub x, and that's in kips as well. So remember that table I did, and if not, again, I highly suggest going to that 3-part video on seismic design. We really get into the nitty-gritty of all this stuff, but roll with me here today. Let's keep on pushing. Levels, 1, 2, 3, yada yada, let's get to the bottom. And then of course, we're going to do summation at the bottom, if I didn't draw it like a 2-year-old. And of course, we're going to do summation at the bottom. Wx, so that is our, that's our seismic mass per story. And it's going to go, so if we shoot back up at the top, we'll see it's broken down per story here, yada yada, dot dot dot. So we're going to input that. That is our small Wx for each story. So let's go plug all those in. So it's 1,500 kips for each story besides the roof. All right, let's do it. Level 1, we're going to say 0 because there's nothing. 1,500, and I'll see you at the bottom. Summation, 18,500. So we're good there. H sub x is the relative story height to ground, and we know that each story is 13 feet tall. So ground is 0, 13, 26, 39, yada yada. I'll see you at the bottom. Now, Wx times Hx raised to the 1.5, which is our k value. Well, if we go across, that's just 0. The top one's easy. 0, 0. Level 2, that gets us 70,308, and we'll go from there. So it's just plugging in these two values into that equation, and let's run it down. Be nice to use a nice little Excel spreadsheet if you have one. Maybe just pop that equation in and let it run, or make this whole table and let it run. All right, I'll see you at the bottom. And our summation is going to be 16,492,965. Forgive me, I did that by hand, and that was stupid. Definitely do it in an Excel table. I know I have one of those now. If that's slightly wrong, I apologize, but it's just the summation of everything in that table. So now, and you know what, I'm going to mix it up. Sorry about this, everybody. We're going to do one more. So we're going to do CVX, and that's just a number. So there's no units involved with that. And then we're going to do FX in kips. And CVX, we know if we go above now, is this here. So it's just this number at the story that you're at divided by the sum. That gets you CVX. So it's basically, it's the ratio of the portion of the base shear that's distributed to the story to get you your story shear. But it's that ratio of 1, as you'll see. So let's get going with plugging that in. So the first one, just so everyone's paying attention, is going to be 70308 divided by, what did we say, 16,492,965. That's going to be 0.004. See if x is 0 here, and we'll work our way all the way down. Here we are. Once again, I kick myself realizing so much. Wow, you should do that by hand. All right, and now fx is just CVx times your base shear. And our base shear is V, which we know is 736.3 kips. All right, so the first one would just be 0. The next would be 0.004 times 736.6 kips. 2.95, and I'll see you at the bottom. And the summation of all of those should equal the base shear, V. So let's see. And the summation is 736 kips. It's slightly off, and I rounded in here, but if you did do a perfect Excel spreadsheet, those should all stack right up to equaling the exact sum of that number. So I'm good with that. Doing it by hand, I'm good rolling with that. All right, and that is our lateral force, F, at each story. And we're going to actually graph that out. So what you have going on here is this. So we've split our building here, and it actually, now we can distribute all of our lateral forces to each story, like so. And there you have it. And what's happening is, in reality, it's not 0 at the bottom, but there's no force acting at the bottom. You have the entire base shear counteracting V, which equals 736.6 kips. So if you do your summation of forces in the Fx area, we're going way back to original statics here. Like I said, everything breaks down to statics. You have the sum of all these forces should equal, because they're all moving from left to right, that means you need a counteracting force, which is your base shear, that's moving from right to left. So your Fx forces sum out to 0, so they're balanced. So we know we're good here. And then what's happening is you have all of these forces moving left to right, and they are creating a moment at the base. And we're also going to include, it's going to be handy here, a shear diagram. We're going to call this story shear, and that's going to be represented in kips, and it's going to look a little something like this. Let's see if I can do this well. My God, this takes so long by hand. Okay, we get the following kind of doodad looking. Look at, we went off the friggin' chart. That's how much we're rolling on this. All right, there we go, like that. And what you'll see is actually this. And then you add the story above to the story below. And there you go. You see that, how that lined up? So that's our shear diagram, if you will, turned on its side almost. If you don't really want to do this, but it's a good way to first simplify in your head. So a high rise is you can kind of think about it like a cantilever sticking up out into the sky, and the cantilevered portion is coming from the ground, and then your lateral forces are like your loading being applied to that cantilever. So if you were to turn that whole skyscraper sideways, it would look like a cantilevered beam coming out of a wall. So you can kind of think about it like that. So your base shear, that is your maximum shear. So like you would in a cantilevered condition where you have, something just like this, which looks very eerily similar to that. And you know that your max, your VU shear, and on top of that, your moment are both at the base reaction. So that's what's going on here when you first want to think about that. So now that we have all that drawn, the reason I want to draw that is because question 2 is the overturning moment at the first floor due to seismic loads only. Well, what you can do is you can take moment, story 1, equal to the summation of 13 stories, I have 2 of Fi, so that's your Fx times Hi, which is your story height. So it's just each one of these forces, your Fx forces at each story, multiplied by that height up to that story. So, that's your first one, and then you got this one, and then you got this one, and yada, 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 yada. I am not going to go through that by hand. I'm just going to get you to the end here. But that's how we do, because it's just, that's how we do. Because in reality, it's just you're building here, you have a force, you have a force, you have a force, etc., and its moment is just force times perpendicular distance. And that's our perpendicular distance is just the story height. So that's all it is, all the way up. So that gets us 87,051.4 kip feet. So that's a pretty large moment there. But that is going to be our answer for number 2. And then, so number 2. Number 3, we want to calculate the overturning moment at the 4th floor. Now what we can do is we can use the value for MO1, which is this one right here, and take the area under the shear diagram to get the change in moment from the 1st floor to the 4th floor. So that's kind of a nice little trick here. And so what we'll do with that is just, that's the total. And now we'll subtract, and we'll use our shear diagram. So we're going for the 4th floor. So we do 736.6 kips, that's the base shear, times 13 feet, minus the next one up, so 732.15 kips times 13 feet, because it's just the story height. It's not, we're not using our story forces, we're using the shear diagram for this, minus 723.13 kips times 13 feet. That gets us 58,554 kip feet. That is the answer to number 3. There you have it. A little bit of a longer one today, not quite a midweek mini, but really, really helpful. It was a team member suggested problem, so that's always the most critical and most important. It moves up the list the fastest because it's for all of you who are asking questions. Thank you for the suggestion. I think it was a great example. I learned a few things. I also learned why I don't do this by hand. Definitely set up a spreadsheet, but always check by hand at the beginning when you're building that spreadsheet. Like and subscribe, leave some comments if you have questions, hit that notification bell if you want the up-to-date on all of my videos that come out. We're pumping them out lately, so it's been really good, really fun, and keep giving me more suggestions. I mean, that's the number one thing with me. So until next time, this is Rich with Kestava, and I will see you guys later.